Well, I'm glad we got that worked out.
Yeah.
I think it was having trouble recording them when we were using the phone, so this will help for recording these things.
Okay.
Okay. All right. Looks like we're looking at a lot of inverse trig functions here.
I think so, yes.
Yeah. Okay. Let's talk about the derivatives of a trig function. Briefly. Okay, if the three trig functions they tend to start you out with are the arctangent.
Okay.
So the derivative, hold on a second, I got it right. We got to go this way first before I can go the other way. So we'll start with arctangent. If I take that, I get 1 over 1 plus x squared. Okay. Now that's similar to what we're looking at in that first problem. In other words, if I said, what is the integral of that? What would the answer be?
Arctangent.
Arctan of x. So
Right.
what we've got to do, there's a trick on these. I just got to remember what to do. Let's see. I can divide top and bottom by 2. So that would turn it into this. Right?
Right.
Now, actually what I wanted to do was divide top and bottom, I think, by 4. So on the top, we're going to have that. And on the bottom, we're going to have this. Now, how does that help? Well, let's see.
Aren't we trying to get it into 1 over a squared plus x squared?
Well, yeah. In other words, if you look at the arctangent, it's u prime over 1 plus u prime. In other words, it's really, if you have the arctangent of u, in other words, and you take the derivative of that, you get, instead of 1 over 1 plus u squared, you get u prime over 1 plus u squared.
Okay.
Okay? Just applying the chain rule. In other words,
Right.
if u is something like x minus 1 or something, it's something other than just x.
Right.
So we're trying to turn this into this. Well, if I let u be 2x, no, I need u to be 1/2 x. This will work. I'm going to let u be 1/2 x. Now, notice what this becomes. this becomes u prime, which is 1/2, divided by 1 plus 1/2 x squared, which is x squared over 4. That's exactly what we're looking at right there.
Right.
So the integral of that is arctan of 1/2 x plus c.
Okay.
A little tricky how I got there. I kind of had to go both ways, back and forth for a moment. But
Right.
I got it. In other words, if we start with arctan of 1/2 x and we take the derivative of it, we'll get this. 2 over 4 plus x squared.
Right.
So that's what you're trying to do in all of these, is somehow come up with a function whose derivative is going to equal what you're looking at. Okay, now which inverse function does that look like it's the derivative of?
Arcsine.
Arcsine. Arcsine of u. If I take the derivative of that, I get u prime, just like the other one, all over the square root of 1 minus u squared.
Right.
So what would be a good thing to let u be?
Could u be 4x or?
Well, we know that this is u squared. So
Right.
letting u be 2x. Let's see what happens when we let u be 2x. Doesn't quite work, does it? In other words, if u is 2x, then the derivative, I would have a 2 in the numerator. That'd be square root of 1 minus 4x squared. But I don't have a 3 and I don't have a 9. Let me think about this for just a minute here. That does happen to be the difference of perfect squares. I don't know that that's going to help us any. How am I going to get a 3 down there? I think I want to divide everything by 9. So that I'm going to write this. Yeah. If I divide the top by 9, no, let's divide everything by, hold on a minute. If I take a 1/3 out of that, hold on. I've got to remember how to do these. It's not going to be the inverse. What's the third one that they give you? The secant? No, hold on a second. I'm looking at it right here. It's the no, it is the secant. They start you off with sine, tangent, and secant, or your three primary formulas that you need to remember.
Yeah. Our teacher hasn't taught us anything other than sine and tangent.
Okay. Well, it doesn't look like I see anything else on here anyway.
Okay.
So that's fine. I don't want to spend too much of our half hour doing guessing in the dark to see how I can figure out how to make that come out right.
Yeah, we could skip to 4
Yeah, I
because
think we
4
should.
seems like
I think we should. Let me just give one extra thought here. If I were to divide that by 9 and that by 9, and then take a 3 out, I think I can do that. Yeah, which turns this into, let's see, I've divided the bottom by 3, so I got to divide the top by 3. So I end up with 1 over 3 times the square root of 1 minus 4/9 x squared. This is going to work, I believe. So u would be the square root of that, which is 2/3 x. So if I say u is 2/3 x, in other words, I take the square root of that term that I know has to be minus u squared.
right.
So now I'm close. Now, yeah, I'm gonna, no, let's see. The derivative of u, which goes in the numerator, would be 2/3. But then that 3 would go all the way down to the denominator. So it would look like that. Unfortunately, that's not what we're looking at. We're looking at 3 over that. There's a section in the book that does these. And
Okay.
I could take 5 minutes to look it up to see how to do it. But I'd rather not do that now. Let's come back to those the next time we have a session.
Okay.
I'll know how to do those. Okay.
I'll circle them.
Yeah. So let's go on. The integral of inverse sine.
And that's what we just did.
No, I'm doing number 4.
Right. Well, I'm saying you
Yeah,
you
but
did.
there's a difference. Inverse sine is the integral of the inverse sine. How would you do that? And is that the same as the integral of 1 over cosecant? I believe it is. So we're really looking for... No, I'm sorry. That's not true at all. All right. Let's do number 5. What method are we going to use for number 5?
Integration by parts.
Yeah, you've got basically 2 different types of functions being multiplied together. Okay?
Right.
So we're going to start with the integral of x squared natural log of x dx. So what's u going to be?
U will be ln x.
Yeah, use log poet. In other words, the first, if you have a log function in there, that's the very first thing you make u. Okay? What's dv equal to?
X squared.
X squared dx. In other words, everything else.
Okay.
Okay? And now, what is v equal to?
X to the third over 3
And,
dx.
No, just that. In other words, if I bring the dx over to the left, or I can just integrate both sides. When I integrate the left sides, it turns into v. When I integrate the right side, it turns into x cubed over 3.
Okay.
What's du equal to?
1 over x dx.
Yeah. Which makes, I'm going to do it my old way. Actually, I'm not. I'm just going to solve for dx. And that's equal to x du. Voodoo. No, we want to leave it like this. Sorry. I don't mean to confuse you. Okay. So now we're ready to write what that integral is. So the integral is equal to uv. Which uv?
ln x times x to the third over 3.
I'm going to put the polynomial first just because it's less likely to be misinterpreted.
Okay.
In other words, if I put the log first, then you don't know whether the x cubed over 3 is part of that argument or not.
Okay.
So if I put it out in front, it's more clear. So that's uv minus the integral of voodoo.
So that would be x cubed over 3
times du. What is du?
Times 1 over x dx.
And that is something we can do. In other words, that integral ends up being x to the third over 9. Is that right? That happens. And then x to the third divided by the new denominator. So that's x to the third over 9.
Right.
So that's the final answer would be x cubed uv minus x to the third over 9 plus c. Okay?
Right.
Relatively straightforward by parts.
Right.
All right. Well, I'm glad I finally found one I could do. Actually, I got that one right, didn't I? Yeah.
Yeah.
Okay, let's look at number 6. Again,
I believe
we're going to use integration by parts. Whenever you see multiplication of two different types of functions, here we have a polynomial times an exponential.
Right.
Okay. So if I rewrite it, x cubed, that's e to the 2x?
Yes, sir.
Yeah.
Yep.
Okay, what's u going to be?
E to the 2x, or it could be either.
Log poet, p is for polynomial.
Okay, so p would go first, so x to the third.
Yeah. And dv?
E to the 2x.
dx. Don't forget that dx.
dx.
Okay. So over here, du is equal to 3x squared dx. And v is equal to what?
1/2 e to the 2x.
Good. Just to check that, if we were to take the derivative of that, it would be e to the 2x times 2, getting rid of that 1/2. So we did it properly. Okay, so what's our final answer? The uv minus all the other stuff?
Yeah, uv minus v du, or the integral of v du.
Yeah.
So
x cubed is v. I'm sorry, that's u. V is
1/2.
So there's uv minus the integral. What's the rest of it?
Minus the integral of v du, so that would be 1/2 e to the 2x times 3x squared dx.
No, VD. You're right. Sorry, my mistake.
And wouldn't you have to do integration by parts again with that?
Yes. And that's what happens when you have a polynomial, is every iteration reduces. Notice we're now down to an x squared in the integral sign.
Right.
Okay. So one more iteration is going to bring us down to x.
And then another one
One more iteration after that, we're going to solve it.
Right.
Okay. Now, these get unbelievably complicated. Here, let me, I don't know if we want to spend all of our time going through all of this arithmetic or not. Maybe just on this once, at least just do it. We'll do a second iteration.
Okay.
What ends up happening when you do a lot of iterations, you end up with a super long algebra line with tons of negative signs.
Right.
So here's what we got. I'm going to start as far left as I can. Minus. Now we're going to do the whole thing over again. So what's u going to be?
U would equal 3x squared.
Yeah, just to make things a little easier, let's take that 3/2 outside the integral sign, like that. That's okay. You can always do that. You can always take numbers out. You can't take variables. But that takes that out, and it takes that out.
So then u would equal x squared.
So, yeah, if I put that 3/2 right up here, and now we do the whole thing based on that. So uv is x squared. V again, I believe, is e to the 2x over 2, right? And nothing's changed.
Right.
E to the 2x over 2. So there's my next uv minus the integral of voodoo.
E to the 2x over 2 times x squared dx.
Let's see. V was e to the 2x over 2, right?
Yep.
E to the 2x over 2, that's V, times du, which is 2x dx.
Oh, yeah. 2x dx.
Yeah. So, that's what we're looking at now.
And then you take it again, and then you get a constant.
One more iteration will knock that x down to nothing.
Yeah, I'm assuming on the test it's going to be multiple choice for integration, so I don't think that we will have a problem that you have to just keep going.
Yeah, I wouldn't think they would give you a test where you'd have to do 4 iterations either. Yeah. They do teach a method of doing like 8 iterations. And there's a pattern to it where you take the derivative of one side, the integral of the other, and you just go down and you find your answer at the end. Have they taught you that method?
No, they have not.
Okay, well then I'm not going to.
Okay.
And this is the way I would do it anyway. In fact, I would have to look up that method. So if I was doing this from scratch and my life depended on it, I would just do 4 iterations.
Right.
Okay? The biggest problem you have is you end up with like 6 minus signs and lots of different brackets. I mean, you can kind of already see that it's getting really complicated.
Right.
This minus 3/2 has to be distributed to both terms, which means this is going to turn into a plus. So you end up with lots of minuses, lots of pluses, and boy, you have to be super, super careful to keep everything straight. I almost can't do it on this page because it's not wide enough. Seriously. But that's what you end up with is a super, super long answer. One more iteration will eliminate that last integral sign, and that's our goal. In other words, we don't want an answer that has an integral in it, unless it's like the kind I described to you the other day, where you can stand an integral if it's the same integral that you started with, because then you can add it to both sides, and you got two of them, and now you've solved it by just dividing both sides by 2.
Right.
But this one will produce an answer. It's just, I say, let's go on. Is that okay with you?
Yeah, let's go on to number 7.
All right. All right, this is fairly straightforward. What method are we going to use for number 7?
Partial fraction decomposition.
Yeah, because you can see that the denominator is the product of two things.
Right.
What is it? X what?
X, so X minus 2 times X minus 3.
Right. Okay. So the secret here is, for the moment, let's ignore that integral sign. Let's deal with just the partial fractions. You always start this off. If I have 2 things being multiplied in the denominator, then I'm going to need 2 partial fractions.
Right.
If I had 3 things, let's say this was x minus 3 times x minus 2 times x minus 1. Then I'm going to have an A, a B, and a C. In other words, if you had a third thing, I would have that, like that.
Okay. That's that would be harder. Yes.
It's a little harder. It's not as hard as you might think. You use a little different technique. This technique we used the other day, where we let A and B, or we let X be a certain thing. We're going to use that technique on this one too, just because this is an easy one. So what's my next step?
Multiply the fractions out so
Actually not. The next step is to add those two. What do you get when you add those two? How would you add? So you'd come up with a common denominator.
Oh, yeah.
Common denominator is going to be x minus 3 times x minus 2.
Right. And then
what's the left numerator going to be?
The left numerator would be x minus A times x minus 3.
Right. Actually, it's x minus 2. In other words,
A times x minus 2.
This has to equal this right here.
Right.
And it does now. Okay? And this one's going to be b times x minus 3.
Right.
Okay? Now, on the left side, I've got 1 over x minus 3 times x minus 2. So these denominators cross out, and 1 has to be equal to ax minus 2. No, let's not do it that way. Let's use the technique we used before. What's a good number to pick for x?
2.
So when x is 2, what is b?
-1.
Okay, so we've solved for b. b is equal to -1. And when x is 3, what is a?
A would be 1.
So now we go back up. And a is 1, and b is -1, which makes that minus. Okay. Now, I don't know that you necessarily have to do this next step, but I'm always a little bit more comfortable if I do it, and that is to check. If I truly subtracted those two fractions, would I get the thing on the left? Well, I would certainly have the common denominator, correct?
Right.
And then I would have x minus 2 on the top numerator minus x minus 3 on the right fraction numerator. Notice what that turns into, plus 1.
Right.
So, I've got it right in terms of breaking up the partial fractions. This is, so far we haven't done any calculus. This is just partial fractions, which
right.
I've actually seen taught in 6th grade, believe it or not, once. I had a 6th grader who had partial fractions, which is really, really bizarre because the very first place you ever need partial fractions is in Calc BC.
Yeah, I haven't learned until...
Yeah, there's no math between 6th grade and what you're in that uses partial fractions.
That's crazy.
Why it's being taught to a 6th grader, I don't know. Okay. And now we put our integral sign back in, and the integral of that is equal to the integral of that minus the integral of that.
Right.
So what's the integral of 1 over x minus 3?
Ln x minus 3.
Minus what?
Ln x minus 2 plus c.
Well, let's not add the c yet. We have log expressions being subtracted, which means I can turn that into one log expression using your rules of logs.
Would that be dividing?
Uh-huh. The x minus 3 over the x minus 2, and now I add my c. So there's your answer. Okay. Let me just explain it because we're kind of out of time here. This method I used where I let x be a number so that I can make a go to 0 and b and x be another number to make b go to 0, and that allows me to solve for a and b.
Right.
That won't always work. Sometimes you're going to get one that's a little more complicated, in which case what you end up doing is the following. This just take a second. Let's say my numerator over here is x squared plus 2x minus 3 on the left. And on the right, I've got a times x squared plus b times x plus c. Now you match up coefficients. In other words, if this is, remember, this is my left numerator, not the denominator. And if that is equal to ax squared plus bx plus c, well, then a has to be 1, b has to be 2, and c has to be minus 3.
Right.
So that's the second technique that occasionally is needed on integrating by partial fractions.
Okay.
You won't always be able to take that easy technique that we used the last couple times.
Right.
Now, we'll end for today.
Okay.
Is this the sheet you're going to want to work on the next time?
Yes. Well, I'll say.
Here's the problem. If I go ahead and solve these ones I didn't know how to solve, and then next time you got a whole nother sheet, you see what the problem is going to be?
Yeah, I will save these problems. Number 2, 3, 4, 8, and 9 for next time.
Okay, we'll just do it that way. and I will look at them and figure out how to do them. I'm sure I can figure it out. They've got lots of examples in the book on how to handle things like that. This one down here puzzles me a little bit more. I'm not quite sure
I
how
don't.
we're going to do that. I'm not sure I know how to take the integral of the inverse sine of x. I know how to take the derivative of the inverse sine of x, but I don't know if I know how to take the integral of it. I may have to see if I can find an example on that one. But anyway, for now, I will let you go. John, have a good evening. Talk to you next time.
Well, talk to you next time.